Streamed 5 seconds ago. What is that?
Looks like it just has the wrong preview.
Can I just smoke in here?
That's fine.
Where?
Alright, cool. We're live there. Let me go ahead and share it. Streamed 5 seconds ago. What is that? Oh no, I don't want to hear myself.
That's the wrong preview.
Alright, we'll copy that jam. That's fine. Alright, cool.
I don't want to hear
We're live
myself
there. Let me
talking.
go ahead and share it. Streamed 5 seconds ago. What is that? Oh no, I don't want to hear myself.
That's the wrong preview.
That's why I don't want to hear myself. Alright, we'll copy that. Mute. Alright, once I get this link up in the study group, then we'll get down to brass tacks here.
Get down, get down.
That's why I don't want to hear myself. Yeah, so stop making me hear. Down the brass tacks here. There we go. Boop, boop. Now I don't have to hear myself. There we go. Sweet. I don't know how well this thing's gonna stream with the Wi-Fi as bad as it is. Dropped frames. There we go. Boop, boop. Now I don't have to hear myself. There we go. Sweet. I don't know how well this thing's gonna stream with the Wi-Fi. Alright guys, let's get this show on the road here. I don't know how well this thing's gonna stream. Alright, so who can tell me what happens
I don't know how well this thing's gonna stream.
we use the tattoo machine? What happens when we put our foot on the pedal? How does the tattoo machine work? Alright, so who can tell me what happens
I don't know how
when
well this
it
thing's
turns
gonna
on
stream.
the magnet tattoo machine? What kind of magnets when we put our foot on the pedal? How does the tattoo machine work? Alright, so who can tell me what happens
I don't know.
turns on the magnet tattoo machine? What kind of magnets when we put our foot on the pedal?
It's a magnetic force.
Okay. I'm going to go ahead and just get to the point then. Alright, so I don't know if any of you did like in school or if you ever tried the experiment where you take a nail and you wrap wire around it. Okay? That's how you create an electric magnet. So they have an iron core. And then we have wire that's spun around. All right, so tell me what happened around it at that pace that creates the magnetism. Okay, so unlike normal magnets that are sort of inert that require any sort of electricity, that's how you create an electric magnet. So they have an iron core. Okay, so normal magnetic material that's spun around. All right, so tell me what happened at that pace that creates the magnetism. Who can tell me where the original coils come from for tattoo machines? Electricity. That's how you create electric magnet. An iron core. Okay, so normal magnetic wire. Alright, so tell me what happened at that pace, activate it, now who can tell me where the original magnet coils come from for tattoo smartass society? That's how you create a tattoo magnet iron core. But that's where they use the original train. Look at it. Alright, so tell me what happened at that pace, activate it, now you just look at it. Who can tell me where the original magnet coils come from for tattoo smartass society? That's how you so we have several components to our modern tattoo trade. Look at it. So tell me what our electrical system activate it. Now you just look at it. Who can tell me where the original magnet coils come from for tattoo smartass society? That's how you
So we have several components to use our modern tattoo trade. So we can tell you our electrical system should activate it. So you just look at it. We can tell you where it's so we have several components to use our modern tattoo trade. So we can tell you our electrical system, stuff like that. So basically, the main just look at it. We can tell you where so we have several components to use our modern tattoo trade. So we can tell you our.
All right, there we go.
All right, so what happens when we push the pedal? Okay, it sends electricity to the coils, right? All right. I know it seems like really like pre-K that I'm like kind of driving this home, but you need to be able to express what's happening. Number one thing people are going to ask you, how the hell does a tattoo machine work? So you need to at least convey that level of knowledge with some level of proficiency. So, you touch the pedal, okay? That opens up the circuit, that sends electricity to the coils, okay? And then what happens? So electricity is now in the machine. What's happening in the machine?
Pulls the arm bar down.
Okay, it pulls the arm bar down, okay, because it creates that magnetic field. It pulls the arm bar. What happens when the arm bar gets pulled?
The circuit's broken.
Okay, circuit's now broken. What happens to the arm bar?
Goes back up.
Okay,
The
so
resting position.
right, the spring, the mechanical element pulls it back, goes into its resting position. So the circuit was broken when the arm bar left the contact point. All right, that's where the actual area here, where we're working with the electrode basically touching the spring. The moment it comes off of that, it is now no longer part of the circuit. It is purely the resonance or the leftover, magnetic force that is pulling it, and then it is now being pulled back the other direction. So an electromagnetic coil machine, oscillates. Basically, it turns on and off. Okay? So when we look at, say, like an icon meter, or you see the term cycles per second, that's how many times it turns on and off. Okay? So we'll later be exploring oscillating relays and diagnostics, how to basically use that to our benefit to understand more about the machine. But what we're going to talk about today is just going to be our basic machine anatomy. Okay? So what I want you guys to do is I want you to get your machine. I want you to get a piece of paper and a pen, something to write with, pencil, whatever the case may be. And what we're going to do first is we're just going to strip down our machine, and we're going to circle out, just make a diagram of each one of those parts that we have, the same way that we have our exploded diagram in our Huck Spalding A to Z. So we're going to move down here. All right, so like we talked about before, when the machine is on, the circuit is completed through the contact points. The coils become electromagnets or electric magnets. All right, the current flows through the machine. Okay, so bear in mind the quality of the metal and the type of metal is going to affect how those coils run. Chris, we talked earlier about how electricity can be lost in elements such as the power supply, the cords, the wires, as well as the frame of the machine that you're using. Okay, so different materials function differently. Iron is a highly sought after material because it's very conductive. Okay, steel is good but less sought after. Okay, aluminum is not really that great, but it works okay. I do believe that you still need to have a yoke, a steel yoke, which is basically a binder piece that's going to hold your coils together, so you still have something that's carries the electric current. Brass is very sought after. However, brass, you still need a yoke. Other materials you can even get as far as a plastic machine, but you have to have an iron yoke binding the coils together. All right, Cuppy, do you not have your machine? Or I gave you machines. All right, Cup. All right, Cuppy. Actually, you come over here. You can use this, be over there. You can be taking it apart for the demo there as well. All right. So who can tell me where the capacitor is located?
Between the coils.
Right. Okay. What does the capacitor do? Okay.
I know a lot about that.
All right. So the capacitor, essentially, the best way I can explain what a capacitor is the capacitor takes the electricity almost like a bucket or a cup, okay? And so it fills with the electricity to a certain point, and then it tips over and it pours it out, okay? So kind of like if you've seen, I was going to say one of those experiments you see, like, old game Mousetrap, okay? The marble rolls in, it gets into the bucket then tips over, and it passes the marble on. With this, it's more like water, because electricity is flowing into it, it's filling to a certain point, and then it's dumping. So what effect would the capacitor have on the coils themselves? What it's affecting is the rate at which it takes to turn on and turn off, and how much power it's giving. So a smaller capacitor is more like a glass, okay? A larger capacitor is more like a bucket, okay? And so a glass is going to have less power, but it's going to fill more often, okay? So it's going to supply that power faster, okay? So a smaller capacitor is going to be better for something like a liner, okay? Very fast, not a lot of hit, doesn't carry a lot of needles, but it's fast. It's open, close, open, close, very fast, all right? A larger capacitor is going to take longer to fill, but then hit harder. So a larger capacitor might be better for something like coloring, something that you're pushing large needle groups, something that you're kind of slowing the machine down already. You could run the same liner and capacitor at the liner and the shader, or the liner and the color at the same volts, and have two very different running machines. Even if the coils were the same wraps, the machines were identical, every other sense of it except the capacitor. So we'll actually get into playing around later with some hot rodding of the tattoo machines, how the capacitors affect using multiple setups, how to kind of play with the different aspects of the capacitor itself. So the capacitor actually has a very big role in the machine and is often overlooked by most people. So keep that in mind. That's one way we'll easily be able to kind of change out a machine. If you want to speed up the machine and there's just not enough, you can't adjust the timing spring enough, you can't adjust the gap enough, one of the things to check out is the capacitor as well as the coils and the numbers of wraps. Now, who can tell me, I feel like I'm using that segue a lot, but what's the difference between the number of wraps on a coil? How does that affect how the machine runs?
So more wraps make it stronger, don't they? Make it a stronger magnet.
Okay. So the more wraps make a stronger magnet. What else would they take? This is on the conversation we had earlier. Okay. If there's more wraps, what else would it change? It'd be a stronger hit, but what would suffer or what would change as well?
It needs more electricity.
It would need more electricity, and also the speed at which the electricity goes from the one end of the coil to the other end, the iron core. So the time it takes to actually transition from the top to the bottom, okay? And what that does, it affects how much you can get, how many volts, how fast it runs, okay? So if you have a 6-wrap machine, just like we talked about with the capacitor, a 6-wrap machine is going to run the dog snot out of 3s to 7s, like fast for a liner, amazing, 5 volts all day long, right? A 12-wrap machine is going to be able to push like 47 mags, okay? But even at the same volt, probably upwards of like 12 volts, it's only going to be running about 100 cycles, maybe 108, So it takes a lot more juice to get out of it, but you can push more, but it's doing it slower. So it's almost like the difference of a small little engine pushing a little baby car and a very big engine pushing a Mack truck, So it's important to know the difference because not all coils are created the same. It's important to know that a 6-wrap is going to run faster than an 8 or a 10 or a 12, and it's good to know which of those you want to use for different applications. So again, the less wraps, the faster it's going to run, but also the softer, the lighter, it won't be able to push as much. So if you put like a larger Magnum or start running, it's going to bog down the machine, and it's just not going to have that oomph, that you need. So it's important to have a couple sets of coils around when we get into building. We'll explore some different scenarios of how we can take the same frame and how we can build it into several different machines. Make sure to kind of back up this PDF on my other phone just in case this iPad takes a crap on me. All right. They just don't make these batteries like they used to, boys. All right. So now we're going to get into our exploded diagram. All right. So this, at first glance, has a whole lot of stuff in it. We're going to make sure to clarify. What I want you guys to do is to take the machine now that it's apart, and we're going to take a pencil or a pen, and we're going to actually trace out. Now, when you do this, try to leave yourself enough room to actually make your list. So if you want to make a list on one side of your sheet, so you can actually list the items, and then you can draw to the areas that you've traced out your sheet there. So you can do it on here, Cuppy, you can do it on this paper, you can do it on top of that. If it takes more than one page, that's fine. What I want you to do is I just want you to be able to familiarize yourself with the machine. Later, we will have some challenges where we'll kind of just come in and have to work on. That's kind of standard for any tattoo apprenticeship. You kind of come in, your machine's taken apart, and there's one missing piece. Okay, you've got to figure out what that missing piece is. All right, Cuppy, so go ahead and you just want to put these on the sheet or trace them out, or like I said, you could trace them out on there if you want. Just try to make sure that one side is sectioned out for listing the parts and then maximizing it in there. You will need to list, according to this, we're over here at about 29 to 30 parts that we're going to list individually. All right, so after you've made your tracings, I want you to go ahead and on the opposite side of your sheet, go ahead and list 1 to 30. We've got 29 here. I have a feeling I'll find an extra part somewhere. All right, I'm going to put the list up here on the screen. If you have any problem seeing it, let me know. This is going to be your part list. What I'll do is I'll zoom in on the first chunk of them, and then we can kind of go a little farther as you need it. All right, so right now we've got items 1 through 16 up on the screen. The best part of the coil machine, there's a lot of discussion between coils and rotary. I do absolutely love rotary as much as I love coils. Now, the coil is kind of the American muscle car. It is loud. It hits hard. You hear it. You can do virtually anything to it. You can make almost any of it run. I can take any machine and make it run beautifully as long as I know what I'm looking for. As long as I know how to troubleshoot my machine, as we'll go into further later. But basically what we're going to go into, we want to look and make sure that all of our angles are true. We want to make sure that, you know, we have good geometry and a good shape to it. But there are ways that you can mod it. So if you know what you're doing, you can basically turn any machine into a usable machine with the right parts and the right pieces, the right know-how. Unlike a rotary machine, the downside of most rotaries is that you do not have as much adjustability. Some of the higher end models you do. You're now seeing a lot more affordable, kind of what we would maybe say knockoffs, or just bands that really aren't made with as much quality in them. So the downside again though is it's almost like a European sports car. So really the rotary can top out at higher speeds. It can do more, it can be softer, it can achieve more. However, when the rotary is pretty much as is. So much like a sports car, nowadays you cannot work on it in your own garage. So this is why we start to have a difference of opinions between the classics, the purists, the traditionalists that want to, be able to build. I can build a tattoo machine with a trip to Lowe's and a Radio Shack if you can still find them, for a couple of other parts. But otherwise, I can basically get everything you need. You can build a rotary, as many of these folks currently incarcerated have shown us. You can certainly build one out of just about any sort of motor that you have. You can strap it down. But the problem is there's less ability to tweak the rotary. We will get in further when we discuss rotaries into how to really maximize and get the most out of your rotary, and how to kind of exploit, how to basically build a cheap rotary, how to kind of get what each aspect is. But it's a little bit more difficult because the tolerances are different. A coil machine is kind of like a Harley Davidson in a way. You basically are always working on it. It is always falling out of tune. You have a sweet spot that's in it, and the more that you use it, the more it changes. The longer you use the machine, the more the mechanical pieces change, such as the spring gets warmer, and that affects how it runs. If it, from a cold start versus using it for 4 or 5 hours. Also, ever since it's moving, it's eating up the contact point, which is changing your contact gap, which is changing how much time it takes to get from when the circuit has been broken back to when the circuit starts again. So it's a living, breathing entity. It changes as you're using it. So it's important to know what to look for and how to troubleshoot. Has everyone got the first 16 items written down?
I haven't written that.
All right. Is there anybody who needs the next from 17 on for the item list?
Wait, is this in the Spalding book?
Yeah. But I want you to make sure that you actually write it as part of this exercise, because writing it is going to ingrain it. Actually doing this project more so than just looking at it. Obviously, you can just look at the book, you can open it up, and everybody that's ever read Huck Spalding A to Z became an amazing tattooer, right? Because all you have to do is buy a book and flip it open, stare at some pictures, and you got it, right? No, the people that get to the top work for it, and especially this kind of stuff. Art is something that's unique to us, and I'll guide you through some ideas and some concepts to explore and kind of expand your mind. When it comes to the actual craft of tattooing, this is something more universal. This is something that unfortunately most tattooers don't know. It's important to understand your tools. If every time your machine breaks you throw it in the drawer, you're going to spend a hell of a lot of money on tattoo machines, but you're also not going to get the most out of your tattoos, unless you have an infinite supply of really good machines. But you won't know the difference. It does not take a $700 machine to do a good tattoo. It doesn't matter what the tool is. It's only as good as the person holding it. It's only as good as the artist using it. But an artist can also be severely limited by not knowing their tools. If I go to set out to do an oil painting and I have all the tools at my disposal, but I don't know whether I should use linseed oil or, the drying elements or turpentine, or, if I don't know how to use it, I'm not going to be able to do a good painting, you know? And so it's important. I can pick up a tattoo machine. Almost anyone can pick up a tattoo machine and make a mark in the skin. But actually knowing your tools, keeping them not only tuned but also maintained, knowing when it craps out on you, how to quickly get it back up to working speed so you can be happy with the results. That's going to be the difference of being able to finish that tattoo in a timely manner versus getting frustrated, upset, and having to reschedule that appointment. So I absolutely believe that understanding and knowing all aspects of your machine is going to be critical. We're just going to touch base on the basics of the anatomy tonight. We will continue further lessons to kind of build on it. Much like I didn't want to keep beating down, the medical road. So we'll kind of touch on each base, and then each week we'll move to a new topic, and then each month we'll revisit those topics with a little bit more information as well. How's everybody doing on this list over here?
I'm on number 7 right now.
Number 7, Cuppy. Everyone got up to number 7? Mm-hmm. All right. There's going to be a handy little worksheet for later. Once we get past basic anatomy, we will get into geometry. We'll eventually cut springs. We'll learn how to work on your machines, how to get the most out of them, how to pretty much take any tattoo machine and make it do what you want it to do, or best, to figure out what that frame is really meant for. I can't tell you how often I find, liners that have been kind of jury-rigged into shaders and vice versa. There is certain frames and styles and shapes are going to be better suited for certain tasks, and so it's important to know. All right, guys. Well, you guys are getting on that list. I'm going to kind of get into a little bit as far as the machine frames and the parts of the mechanical system or the frame itself. So although many frames look different, they all have basic features. You've got the jaw, which is going to hold the tube together. You can see that this old slit jaw. You can have a guillotine, which kind of has a turning vise on top and a sliding piece that kind of tightens up around it. You also have the old swing gate, which is going to have kind of a mounting at the bottom and then a looser piece at the top so you can get some more in there. But a lot of the machines, particularly like workhorse irons, have all kind of gotten into the jaw with sort of the drilled hole through it and the wing nut on the side kind of look. Lots of companies now you're going to see have the coin and all that stuff, so that doesn't necessarily affect too much. It does make it a whole lot easier to grip. All right, how's everybody doing on their list?
I'm on 13.
Number 13. Everybody got up to 13?
I was right in 13.
You were right in 13?
Yeah.
All right, you got that? All right. All right, so we can kind of see everything up into that point. All right, the base of the frame is where the coils are mounted. All right, that's going to be the 2 bolts on your frame. So if you're done with your list or you have a moment, take a look at your frame itself. So Cuppy has a Paco Rollins machine that has a guillotine style vise. Chris, I believe, has a workhorse iron. What you got there? So you have a jaws or a little split down the middle. Yep, split down the middle. And then what do you got over here? Oh, you ain't even got a. What happened? What happened with Taco? Nah, you're good. Well, this is just a multi-piece. This actually, they do this because it makes their. So this is a flat piece, and then they use a press brake and they bend it. But This guillotine piece, coming from experience, is a much harder piece to bend. So what they did is they milled this separately and then put it on as a two-piece. The downside of this frame is that it's two very different types of materials and metals, so they're going to have very different conductivity. The high polish on this frame kind of tells me it's an alloy as well. So there's going to be a little bit of issues with electrical conductivity, but overall, it's supposed to be a Mickey B, okay, an MB. All right, so it's kind of modeled after Mickey B, which is a really cool machine. Cool, what we got here, so these points here, these two that you're seeing there, that's where your coils are going to be. Did you have a yoke with that, or is this is the conductive material? That's why they have this on the inside. Okay, so this serves as a yoke and the vise. So I'll give them points on creativity there. All right, so Phil, I see you got your list. Did you mark and detail out your machine there? Okay, cool. So that might bite you a little bit later on, but that's okay. We'll get into that in a little bit. The main thing is I want you to be able to put it back in the way that you got it, because there's a couple pieces that are really important that they go back where they were in the order they were in. So there's a couple pieces that are important, and we'll kind of go into each aspect of those here shortly. All right, so the spring brace or the spring seat is basically on the back end of the machine, the farthest low point where your spring is going to mount there. Now, this is an important feature that often gets overlooked. All right, the spring is one of the, it's the only moving part other than it's driving the needle, but it's really getting the most wear and tear. So a bad spring brace can cause lots of breaks in your springs. It can cause, there's actually a specific angle. It's about 6 degrees. It's a slight angle that needs to be on there so it relaxes properly without having to bend your springs. It should be gently, kind of beveled a little bit so you have a little bit of a nice roll without a hard edge. So as we get into hot rodding our machines, we'll look into the spring braces, into the brace for the spring, or the spring seat, or the spring saddle, just depending on what terminology you're using. And that's going to help kind of point you in the right direction for when you're looking at a machine, knowing what a quality machine is going to look like. And generally, you want a little bit of a fatter saddle. It's basically cushion. It's more padded. A thin saddle is going to distribute a lot more of that movement back and forth and cause a higher vibration in that machine. It's going to have a lot more what we call chatter, which basically means instead of it being a nice smooth motion, it's got a lot more fluttering to it. It's not quite smooth as it could be. And that's going to be really related to the thickness of the spring saddle or the spring vise. So again, we've got our jaws or a vise in the front. We've got our base, which is going to be the front portion of the machine where the coils are mounted. Our side arm is going to be where our contact points are. That's the side that bends and comes off to the side. That also contains our spring saddle or our spring brace. And we are going to also talk about our machine coils, which we discussed a little bit earlier. Now, generally, you have either a steel or an iron core, as discussed, that's going to give you the highest quality electromagnetism. If you find that when you take apart a machine, you see shiny cores, which is the metal piece that the wire is wrapped around, if you see it shiny, there's a pretty good chance you want to huck those coils and get a new pair, okay? Because you really want something that's just down and dirty and dingy, because you just want it to be iron or you want it to be steel, but you want it to be as close to its original raw material and less processed, because that raw material is what has the magnetism in it. It has the most amount of earth, and the more processed it is, it has the less earth and more shine, it has more of that artificial quality, and it really does show in how well the machines hold. The same is true for armature bars, because they need to be magnetic. So you want a nice, darker armature bar is always going to be a good sign as opposed to a shiny armature bar. Okay, there are ways to just make a chrome one black, but generally, if you're just looking on site, a darker armature bar usually represents the material is more of a raw steel or iron, and that's going to serve you a lot better down the line. All right. Our coils, as discussed, we can have, generally they come in even wraps, so you have 6, 8, 10, or 12. I have not seen anything too much larger or smaller. So those are basically going to be those. The coils are going to act like electromagnets. They are attached to the base screw, which is part of the electromagnet system. By that system, they are now using the frame to carry the electricity as well. So it's important that your frame material is good. You can get around it if you have a yoke, which is a binder piece, which is kind of like how your vise is working as a yoke. And what I mean by that is it's giving it an electrical connection and a magnetic material, because the rest of your frame doesn't have that. So it's better to have a solid, simple system. The more pieces, the more parts, the more processed or shiny or whatever the machine may be. If you have a brass machine, everybody used to love brass because brass, it's a little softer, so it absorbs a lot of that vibration, and people just assume that the brass had a better conductivity because it's assumed that brass and copper, the electricity goes through it better. The problem is that it's non-ferrous. So it's not a magnetic material. You have to have iron as the yoke. And so because you have to have that piece anyway, the only part that's really transferring a lot of that electricity or the magnetism is that yoke, and then it's changing to go on the surface of the brass or copper to get the electrical component. Instead of passing through the machine, it's basically just at that contact point. So ideally, when you're working with a frame or a machine, you want iron or steel, okay? All these other things, brass, gold, whatever the crap that is, plastic, is all junk, all right? Just take it from me, it's all junk. It's heavy, and it is not conductive, and it will work, but it will not work to what it should be for what you're paying for it or what you're using it for. Of course, our machine springs. So we're going to have our front spring. Generally, when we talk about the front spring, that is your topmost spring or your kind of skinny triangular looking spring. They come in lots of different fashions. Some have a little silver contact point. I think that's kind of old school nonsense. That's like 80s nonsense, really. That's just so that you don't eat a hole through the spring. Back in the day when we used to use these power supplies we called the nails, that just were just these heavy power supplies, you were putting so much juice through that thing, it was literally eating a hole in the spring. Partly that's because the materials they reused kind of sucked. Nowadays we use either blue tempered steel, strap steel. It's a little bit more durable. It has a better conductivity. It lasts a lot longer. There's no need to get a spring with a contact point in it, because that contact point is where you're going to have a disruption in the smoothness of that movement. So you want to make sure that you have preferably a dark blue tempered steel, a strap steel. We'll get into cutting those as well. But again, same concept. Avoid shiny. Okay? If you see it and it looks really shiny, it's probably a polished piece of crap. It's a polished turd. Okay? If it looks dark and kind of, beat up and just not that fancy, that's a diamond in the rough. You know what I mean? Always choose the more basic matte finish. If you get something polished and fancy, it's usually junk, okay? So we get into our springs. Our rear spring is going to be critical. It is not just connecting to the spring saddle. It connects with the armature bar, the spring saddle, the front spring, and it is an integral component in how long it takes, how hard it hits. We'll get into kind of specifics on springs, but there's so much stuff to talk about just on springs that we have our own seminar just for springs. That's how fucking important springs are. Because other than coils, the only thing working in that machine is your spring. So you have the most room for play, but also the most room for error, the most room for problems, okay? So springs are very important. I want you guys to not only be able to know how to identify what spring you need from, the basic kind of tool set, but also how to cut springs and make them what you need out of that. One, it's integral to know. It's going to give you some bonus points with those old school heads, but it's also critical that you understand how it affects the machine, and so that you can understand, hey, I want to create an effect. So if I adjust my springs, I adjust the thickness of my springs, I adjust how they run. So the gauge of the spring, if it's thicker, it's going to be stiffer, all right? It's going to, react differently than if I use a thinner softer spring. Okay, so it's important to kind of go those, and again, we'll get into kind of an in-depth spring seminar a little bit further forward. And of course, we're going to attach those with screws and washers. Be mindful, a lot of problems happen with the washers themselves. So one thing is you have two sides to most washers. You have a polished, kind of soft, rounded, beveled edge, and then you have a flat, kind of more rough, rugged, it usually looks a little crummier, depending on what you spend, because believe it or not, there's like penny washers and there's dollar washers, you know what I mean? It's like anything else, you want to spend that money. Now, contrary to popular belief, most people put the flat or the smoother, rounded side kind of out, facing them, because it looks nicer. The problem with that is it leaves the flatter, more burred up end actually touching the spring. So always face the smooth, polished end to the spring. Okay, that's usually why you have two also. So if you have two washers, you can put the polished side next to the spring and then put the two flat sides together, so you still have a good look. You get more, actual absorbency of the vibration, that's going on, so it's not so crazy in there. But if you have the less polished side onto a spring, it has a single burr, which could be a small little imperfection in that bottom side. That can be the cause of spring breaks over and over and over again. So when in doubt, take the polished side and flip it down towards the spring, because you don't want to have a problem with it later. So you'll notice as you look, you're going to see two distinctive sides on your washers. Now, if you look through your washers, you're also going to see some really skinny washers. Okay, they look like washers, but we call them shims. And what those are basically spacers. Spacers are there so that you can adjust frame geometry. Even some of the best frames have spacers. And the reason for that is just during the process of manufacturing, during the tolerances, you might have a little bit of adjustment to really get that perfect gap. One thing that you're going to notice is your rear spring, your rear spring and your rear coil, so your bottommost coil, okay? So when the arm bar is moving, what's the coil that it hits first? Right, so it's up top, it's moving, what's the first coil it hits? The top one, right, okay? So the bottom one, based on the fact that it's not moving, okay, the bottom coil is stationary, and the bottom of the spring of the armature bar doesn't move nearly as much as the top, right? So if they're both spaced out the same, what happens is it hits the top coil and it still has all this gap behind the bottom coil and the rear spring, or the armature bar that's being pulled on. What that represents is a loss of magnetism or magnetic potential, okay? So if you shim that bottom coil, you put a couple little spacers in there to just get it a little closer. The closer you can get it to that armature bar, the better it's going to run, the more magnetism you're going to get. You'd be surprised when we do our hot rodding the tattoo machine seminar, that little bit is going to make a world of difference. It's a lot of little tiny things that affect how it runs, particularly machine geometry, whether everything's nice, straight, and true, whether things are gapped in there. Imagine trying to ride a motorcycle with a bent up frame. You know what I mean? It's going to be really hard to get down the road. You might be able to do it if you're cuppy the bat, but otherwise, you're going to have a real time riding it. And once you get it up to about 50, you're going to really feel a lot of that wobble and that vibration. All right, everybody's got their list, yeah? All right. So as we kind of talked about here, we've got our basic machine diagram. This is just basically our frame. We've gone into over here. This is where we're talking vise, or our jaws as they're calling it here. This could be our guillotine. This could be our split vise right through here. There's also a swing gate style, which is a national brand, so you're not going to see it on Huck Spalding. It is a patented national. Some people love them. I think they're goofy, but it does allow an easy access, much easier than trying to work in the slotted vise here particularly if you have different size tubes from different companies. Nowadays it's a little more uniform, but back in the day you might get, as much of a difference as a hundredths of an inch, which could affect, especially on this, there's less give. So the swing gate allowed a bigger opening, and basically this whole side would come off. Or you could do the guillotine, which is my personal favorite. Sadly, you don't see it you see it on some really good machines that I love, but you also see it synonymous with a lot of cheap machines. But the guillotine is my favorite. That's similar to like how the Paco Rollins machine is over here. Phil, yours is a guillotine vise as well. You might actually have a sleeve. Let me double check. I think you have a tube sleeve. You have what we call a crusher. Let me see your device here. Yep. Okay, so you have a crusher. What you have is you have a piece of metal, and then you have a wing nut that actually puts pressure down onto that metal and tightens around it. So we call those tube crushers, because back in the day they would literally bend a fucking, a crease in the tube. So it's a sleeve or a crusher. Like I said, I love the guillotines. That's just a personal favorite. Most of the guys nowadays with workhorse irons, a lot of the machine builders, they're doing the slotted vise for one simple reason. It's easy and it works. Okay? I can drop that with a jeweler saw, a Dremel, anything I need. It's that easy. I don't have to do a lot of machining. So when you're doing these and building them at home, you're obviously going to go with, simple and effective. So this is your spring brace or saddle here. Okay, that's the seat for the rear spring. This is where your contact point's going to sit. This is also part of, now this here is not actually part of our electrical system, and I will explain later why. But this part through here where they're connected, this main piece is very much part of our electrical system right here. Right here is another big part of our electrical system, okay? But this point and this point are not part of our electrical system. Chris, can you tell me why?
It's because the wires connect from the contact screw to the coils, and if it ran through the arm bar, then the circuit would be complete the whole time. It's the only way to keep the circuit from being complete, to just ran through that.
Right. Okay. Now, in your washer selection, you also have two washers that are not metal. Okay, these are usually plastic or rubber. You could use a grommet for this. I have. What these are basically called, the fancy word for them is a non-conductive washer. Okay, and so what does non-conductive mean?
Electricity doesn't flow through it.
Correct. Electricity does not flow through it. All right, so you will note that the non-conductive washers are at the top of your side arm where what's located up there? What's at the top of your side arm? Your contact point, yes. All right. I think Chris was trying to throw that your way, and you were like, what? All right, so that's your contact arm, okay? That's basically where your contact post is, your binding post, all that stuff. Lots of different things under a different name. So if you look, that's item 29 or so on your list there, the contact point, also the binders, the binder screws and all that. So as we get through, and make sure, like you guys make sure to hold on to these lists, because when we do the surprise missing part test on your machines, you're going to want to make sure that you've got your list, okay? Because it won't be like, I might let you look through your book, but, for the most part, I think you're going to have to tough it out. All right, so we've got our two binding points where our clip cord connects, okay? So here, this one has a non-conductive washer. So again, no electricity is running through the side plate, okay? So the side plate, theoretically, could be any material under the sun. There's no electricity running through this. Okay, with the exception of any residual electricity through here. But really what you're having is the spring seat here is where the electricity goes through. Okay, now if you look at your clip cord, that's usually where that connects. You have one end connecting through your clip cord. All right, that's going to run through your spring. Let's find our little exploded diagram over here. All right, fine enough. So it's going to run through your rear spring, your armature bar really is going to run through your rear spring to your front spring, and that's going to touch the contact point. Let's see if we can get something a little bit better. We'll speed up to the front part. Let's see. All right. So this section here does not touch the frame. This does not touch the frame. All right. This is where you have electricity running, and it's going to come up and it's going to contact here. That's going to create a circuit through your coils. And when it pulls down, that circuit is broken, okay? And that's what's going to help create that downward motion. And then the rear spring is what's going to pull your armature bar back, okay? So how fast it gets back the other direction is definitely dependent on your rear spring. All right, and again, this stuff right now seems like a whole lot of, a lot of information without a lot of gusto, but as we get into it, you're going to understand how this stuff functions. It's just more than we can cover. I could sit here all fucking day and barely touch the surface on building these machines. So we're going to spread it out throughout the process. All right. And so we've got our coils and our machine breakdown. Let's get into our... My iPad died, so I'm looking on my phone as well so we can kind of pull up. All right. So here's what I'm talking about in terms of, here's your clip cord. Okay, so nowadays we have clip cords, RCAs, 1/8-inch phonos, all different ways to make the same thing happen. We're basically applying positive and negative electricity to the frame. Okay. Right through here, you'll note the two bottom pieces where the machine is going to connect. Okay, so your clip cord is going to connect here on the binding post. This is called your rear binding post. This is going to be your top binding post. I could be saying this totally backwards, but you know what I'm fucking talking about. Alright, so in through here, this is where that connects. Again, we have the non-conductive washer, so it is not actually touching the side plate of the frame. This clip cord piece is going directly into the frame. So it's directly into because it's going right up through here, through the springs that are carrying that. Okay, so the electricity is traveling through the spring saddle, up the springs to the contact point. That's where it's making connection. The moment it makes connection, that turns these on, and that's going to break that and pull that armature bar down, turning it on and off. All right. So here's the hole in the underside. You see how it runs through and connects. It does not actually have to physically touch the spring. It is passing through the material. If it does physically touch, that's just one step better. But most of them some of them are drilled like halfway. That's not as good, but definitely you want it to touch, but it does not have to. This is going to go into our kind of rear binding post. Ah, look at that, I got it right. All right, rear binding post here. Those are the things that always trip me up. Rear, top, back. All right. So let's see what we got here. We're going to zoom out of that a little bit. All right, so it is critical that you guys spend a little time reviewing these chapters just to make sure we got everything. We'll spin down. We'll take a look at this. Is what we called the nail back in the day. This thing could probably punch a nail through a board on its own right. Okay, it is a very hard, very fast hitting power supply with little to no variance. It basically... You've got 10 volts on this thing, but a slight turn of the knob, and this thing is just, at its lowest volt, this thing was probably still hitting at like 16. Like, it's just insane. But this is what they used to do back in the day. So, and they would actually install these kind of under the counter and then hide the rheostat over here, which is your little switch. And so you'd have kind of the table here, and then it would be like hidden underneath there. There's also, I have actually worked with guys that have worked... there's multiple ways to get power. One of the ways is a car battery. If you have like a car battery on like 2 car batteries and a deep cycle charger on trickle charge, that is one of the best power supplies you're going to get. It's the smoothest, most consistent power supply, but it is far from portable, okay? Which is why we have so many different power supplies on the market now. But back in the day, they used to just have car batteries. I worked with a guy who did for years. All right, so here is our rear power supply. Here's your washers. Again, see how they're doubled up. The larger washer is on the bottom. The smaller washer is on the top. Now, they do not get into specifics, but again, make sure that the smooth side is down, facing your spring, And then if you have two, you can put the flat sides together and the smooth side can go up. But do not let the unfinished edge rest on the spring, okay, because it will break it. This is one of those stupid contact points I told you about. All right, that's some old nonsense that just gets you to buy some other crap. But like I said, when you're running those nails, it made sense. You just don't need it nowadays. We have much smoother, much more consistent and reliable power supplies, so we do not need quite such a setup. All right, here's our armature bar. Again, we want to make sure that this is a really good magnetic material. The armature bar is a really crucial component to the tattoo machine, okay? It is not just the bar that the needle sits on, all right? The armature bar controls how fast, by its weight and its magnetism, how fast it moves when that magnet turns on, okay? So if it's a skinny one, they make speed bars, they make all different shapes, they make top ones, bottom ones, little holes in it, big, all kinds of different shit. There's probably like 100 different bars out there. You don't need all that, but it's important to understand the differences. So if you have, again, a chromoly, aluminum, brass, any of the shit that's non-ferrous or just isn't good electrically conductive material, you're presenting a harder time for yourself than if you just got a good, simple steel or iron bar. So I think that the time's out. Eventually I'll get it right and we'll be like, all right, the TV timed out, it's break time. Don't get your hopes up. All right, let's see. All right, let's get this thing back online. Oh, there, just get a controller for the thing. That would be nice.
I think that's actually in. No, it's for the. It might be for the TV. It might be in the back.
Yeah, if we could find that, that would be super awesome. Sorry, buddy. All right, back in business. All right, so the armature bar, the weight of the armature bar is going to affect how the machine runs. Okay, if it, some of them they cut the weight down by putting slots in it, by putting holes in it. But bear in mind the material again being pulled. If it's a little thicker, it's going to be stabler. Okay, if it's real thin, it's going to have a lot harder time getting through that movement. Okay, if it's if you're cutting too much out of it, if you don't have enough material, you've got less for those magnets to pull on. Okay, so there's a fine line between a speed bar and an inefficient bar. Between having something that moves a little faster versus something that's wobbly and all get out. Okay, so you want really to be concerned with the material in your armature bar more so than the shape of it. You know what I mean? Honestly, the shape couldn't matter. But the height of your armature bar is absolutely crucial because the height of your armature bar is going to affect the length of your rear spring and your front spring because they have to connect to it. Okay? So if it's a very, tall armature bar that's going to have a shorter, stiffer rear spring, okay, which means it's going to have a little bit harder time kind of pulling down, going to create a little more resistance, it's going to snap back a little faster, okay? It's stiffer, all right, so it's going to affect it a little bit more. But conversely, you're also now going to have a taller front spring. And by having a taller front spring, that's going to make a softer hit for your front spring unless you adjust the thickness of it. So all these things play in with one another. No one of them is necessarily better or worse in every scenario. All right, so for certain scenarios, that's going to work better. If I want a softer, slower shader machine, having a very tall front spring is going to give me that because instead of, it's going to sag a little as it hits and it's going to come back a little bit. It's more lackadaisical. If I have a shorter front spring, that's going to run more like a liner. Okay, it's going to be faster on the comeback. It's stiffer. It hits harder. It doesn't sag. It doesn't take a second to get back up. It immediately hits and goes back. Hits and goes back. Okay, and I'm also going to have in that scenario more likely a shorter armature bar, which is going to create a taller rear spring, okay? And the rear spring kind of fights the downward motion a little bit, but it also is in charge of how fast it pulls back, okay? And so if I have a really kind of easy going rear spring, it's kind of long, so it's kind of soft, and it's basically not really snapping it back, but it's kind of just doing its own thing and returning relaxed like. It's not going very quick with it. Now the problem again is if I create too much pressure on that rear spring, it's going to crack. If there's too much movement, it's going to crack. So it's important to have several lengths of an armature bar, okay? Because I will tell you that there's no one specific. There's a sweet spot, but if I'm working on different machines or I'm really trying to get the most out of a machine, what I want the best armature bar for that scenario. Now, if you're talking about prefabs and you're not talking about machining it yourself, you could get away with having a slotted armature bar slot. Some of them you'll see there's a little bit of slotting for a little room to kind of play with that. You'll see slotted rear springs, slotted top springs as far as your timing. So there's all sorts of different things out there pre-made that you don't necessarily have to build yourself, but it's important to know the differences, and we'll get into that as we get into hot rodding the tattoo machines. I'm just kind of want to touch base on some different components of what you're going to see and how things are going to be reflected back as you make each change. That's kind of the problem. It's the good and the bad of the coil, because if I change one thing on a coil, it affects something else on the coil, okay? Unlike a rotary in many respects. When I enjoy the rotaries because, you know, I can adjust things separately, okay? But I can't adjust everything on every rotary, you know? So keep that in mind. You can get away with a lot, you can manipulate a lot on a coil machine, but you are going to be limited, and you have to understand the correlation between, if I go out and I take my little red car out there, my little red roller skate, right? Great gas mileage, all right? Now let's say I go out there and I put monster truck tires on that, okay? That's going to affect a lot of shit about how that car runs, okay? It's not going to suddenly make it a monster truck, is it? It's going to make it harder for that engine to turn. It's going to cause more of my money to go out and gas, you know? It's going to affect how my speedometer runs, you know? It's going to affect my frame. I'm going to have to adjust, you know, the frame, the wheel wells, all that stuff. So it's important to understand that you can tweak a little this way, tweak a little that way, and get the most out of your machine. But when you change one thing, you're changing something else, you know? So they all correlate to one another. And we'll get into playing around with some different ideas on how to kind of maximize what we have a little bit later on. And I want to get through here. We're going to try and at least cover kind of this chapter through here. All right, so where that is, there we go. All right, so, all right, this is our spring position. Now, for the contact point position, it affects where it hits on the spring. So this is kind of more of, I wouldn't say it's a wives' tale. What I would say is it's an old rule of thumb. It's a tried and true, okay? It's something you can easily look at and go, okay, I think that this probably relates. However, it relates for a reasoning that we discussed a little bit on earlier, not necessarily because of the actual position of the spring. It does not matter that contact point, it does not matter what angle the contact point is at, okay? It's delivering electricity. It doesn't matter the angle it's at. What does matter is how much of it touches, okay? So sometimes you'll have them kind of rounded or pointed or smooth. That one there is flat. It's making kind of a flat connection. It's transferring electricity. What it's being set up here is actually more of a conversation about how front spring length affects how a machine runs, okay? So if I move that contact point to touch the top of that spring, all right, I am in essence using more of the length of the spring. I am making that spring act as though it's longer, and by doing so, let's say for instance, whether it's a piece of metal, whether it's a 2x4, all right, let's say I've got a 2x4 that's, you know, maybe 2 feet long, okay? And let's say I've got that same 2x4 and now it's 6 feet long, all right? So if I was to put both of those between 2 points and then walk on them, okay? Now, the 2-foot one probably isn't going to bend much at all, okay? But the 6-foot one is going to bend drastically. In fact, the 6-foot one, I could probably just push on a little bit and you would see a vibration or a wave effect run through it, right? It's going to be springier because it's longer. The shorter one, conversely, is going to be stiffer, okay? If I was to then hit you in the face with those 2x4s, all right, the small, stiffer one is going to have more of an intense, hard hit, and the longer one is going to kind of almost feel like it wraps around you a little bit, okay? It is more of a sag. It hits you, but it kind of wraps a little bit. It conforms a little bit. So when I'm tattooing, a longer front spring is going to give me a softer hit, per se. It's going to give me a little bit more sag on the return, a little bit more of what we would call give, okay? So instead of it just real quick coming back and hitting you, boom, instead of a real fast, a lightweight jab, it's going to give you more of like a heavyweight slap. It's going to be a little bit softer, and it's going to come back through a little bit. It's going to kind of soften the way that goes. It's going to lower the cycles per second. Now, granted, this book was written before cycles per second and oscillating relays was even a thing. So we'll kind of touch base on that later and how those relate. But basically, what I want you to know from this is I want you to understand that a taller front spring is going to give you a softer hit, okay? That's going to be better for like a shader or a color packer, okay? Now, a shorter front spring is going to give you a stiffer front spring, and that is going to make it act faster. There is going to be less time between when it hits back, when it returns to its rest position, and when it immediately comes forward. That's going to boost your CPS, or your cycles per second, higher, which is going to be better for a liner or a fast running, like a gray wash kind of machine, if you like a really fast, because we'll get into that later. But it is important, the thicker your pigment, the slower your machine should run. The thinner your pigment, conversely, the faster it should run. So when you're lining, that black ink is very thin. When you're coloring, that color pigment is generally thicker, okay? So we'll get into correlations between pigment and needles and machine speed a little bit later on. But your spring, your contact point position to your spring is very much an indicator of how that machine was put together, what it's kind of made for, and how it kind of runs. Now, there are different machines like cutbacks, there are tall shaders, short shaders, all different stuff. But it's important to kind of look at this, and if you take nothing else from it, just understand that if the front spring is longer, or you have your contact point at the top of it, it's going to act softer and be a little bit slower getting back up. If you come down to the shorter part of the contact spring, even if there's all the rest of the spring, you haven't made a single cut on it, but you come down to the bottom portion of it, that effectively is now where it bounces. Now, you're still going to have all this extra flop up top, you know, so you still would want to trim it if you found that sweet spot. But by going down lower on the spring, you're effectively making it act stiffer, which is going to make it faster from that rest position. So the taller spring is going to react slower from a rest position. The shorter spring is going to act faster from a rest position. Taller spring is going to be better for shading. Shorter spring is going to be better for lining. Here again is another old rule of thumb. This rule of thumb pertains to gap, okay? This is the distance when you pull down your machine and you're now looking at the distance between your spring and your contact point. Again, they have this weird little bump out thing. That's what they used to really market and push pretty hard. Remember, this book was written by a supply manufacturer, so they're going to tell you that all their shit is the best. But honestly, nowadays, there's no point in having that fillet piece. All right, so the old rule of thumb is that a nickel is for a shader, a dime is for a liner. Now, if you're old and half blind like me, you might as well double those up, okay? I prefer a really long stroke, okay? So one thing to keep in mind is to look at how many millimeters or how thick an actual nickel is. I probably run a 4 millimeter stroke, so that gives me probably about 2 nickels. All right, and I run that on lining and color. You know what I mean? But what it's saying is, so if I have a nickel gap, okay, versus a dime gap, that nickel. All right, let's see. All right, let's see if we're still broadcast there. Yeah. Alright, so we might have lost some of that. That's okay.